Today we're going to develop our kinematic equations. 5 equations we're going to use to help us with solving motion problems of displacement, velocity, and acceleration. So let's dive right in. For our first equation, we're going to start off with our definition of acceleration, which we know is our change in velocity over time. And we know that delta v equals v final minus v initial. So acceleration equals vf minus vi over t. We multiply both sides by t. At equals vf minus vi. We can add vi to both sides and say that v final equals v initial plus at. Straight from the definition of acceleration, we get our first equation. Now for our second equation, what we're going to do is we're going to start off with a velocity time graph. And we know lots at this point about velocity time graphs. So what we're going to do is we're going to put an object on here that's moving at a constantly changing velocity. So it's got a constant acceleration. The rate of change of the velocity is constant. We know we have some initial velocity here. We can label a final velocity over here. And all of this happens in some time period t. Alright, well, one of the things we know about the velocity time graph is that the area under the curve is equal to the displacement. So we can write the displacement as the area under the curve. And how do we figure that out? Well, if I look over here, I actually see two distinct shapes. I see this light blue triangle area, and I also see this green rectangle. So if we add those separately, that should give us the total area under the curve. So we've got an area of a triangle plus the area of the rectangle. Now the area of a triangle, we know the formula for that is 1/2 base times height, and the area of the rectangle, length times width. So we can say that our displacement equals 1/2 base, looks like it's t. Height appears to be vf minus vi, plus length times width. Length looks to be t, and our width looks to be vi. So all we have to do is a little math here. Say that d equals 1/2 t vf minus 1/2 t vi plus t vi. And we can take these two. Tvi minus 1/2 Tvi is going to leave us with 1/2 Tvi. And say that our displacement equals 1/2 Tvf plus 1/2 Tvi. Do a little bit of math here. Looks like we have a couple things in common that we can factor out. D equals t over 2. Vi plus vf. And now let's just take that t and let's divide it out to the other side. We can say that d over t equals vi plus vf over 2. Now, what is d over t? If I recall correctly, d over t is going to be our definition of average velocity. Therefore, we can say that average velocity equals vi plus vf over 2. That is our second equation. And that should make fairly intuitive sense. If we look over here at our graph, between vf and vi, if we have something that's moving at a constant rate, we would expect the average of those two to be halfway in between. And really, that's all that that equation is telling us. Moving on. Developing our third equation. What we're going to do now is we're going to take and go to the same spot we started with on the previous equation up here. Let me circle it over here in purple. This d equals 1/2 tvf minus vi plus tvi. That was working out great for us, so we're going to use the same argument, get to the same place, and start from there. So we'll say that d equals 1/2 t vf minus vi plus tvi. Now, our arguments that we make to move forward are going to be a little bit different. We know that VF equals VI plus AT. That was from our equation 1 up here. That allows us to say that VF minus VI equals AT if we subtract VI from both sides. Well, we can take that and replace VF minus VI over here with AT. Let's do that and rewrite this as D equals 1/2 T times AT plus VIT. Do a little bit of math here. We can say that D equals VIT, I'm just switching the order, plus 1/2 AT squared. And there, simply enough, is our third kinematic equation. Doing good here. We've got 3 down, 2 to go, and the fifth one, I guarantee you, is going to be so easy it's hardly worth writing down. Let's move on. For our fourth equation, and let's actually start this one on a new page. For our fourth equation, we're going to start off with the definition of average velocity. Going to say V equals D over T. And now let's just solve for D. D equals V average T. Now we know already that V average equals VI plus VF over 2. How do we know that? That's our equation number 2. So we can write that D equals VI plus VF over 2 times T. Well, now let's do something a little funky, something you wouldn't normally see unless you knew what you were trying to do. This T here, we can go back to our first kinematic equation where we said VF equals VI plus AT. Let's solve that for T. If we subtract VI from both sides and divide by A, we can say that T equals VF minus VI over A. Well, we can plug that equation in for T, which will leave us with D equal to VI plus VF over 2, all times VF minus VI over A. And we can do a little bit of math here, simplify that. Use the FOIL method for the top, VI plus VF times VF minus VI. And we come up with D equal to VF squared minus VI squared all over 2A. Well, we can multiply both sides by 2A. 2AD equals VF squared minus VI squared. And if we add VI squared to both sides, we can say that VF squared equals VI squared plus 2AD. There is our fourth kinematic equation. And now for this exciting number 5 equation, all we're going to do is take our definition of acceleration, change in velocity over time, and that's it. The definition itself is our fifth equation. So to sum up, what are our 5 equations? First, we have VF equals VI plus AT. That came straight from the definition for acceleration. 2, we had average velocity equals VI plus VF over 2. That came from our graph, although there are other ways to derive it. 3, we had D equals VIT plus 1/2 AT squared. 4, VF squared equals VI squared plus 2AD. And 5, A equals delta V over T. And 5 and 1 are really the same thing, just written in different ways.